Hello everybody, welcome to today's COSI seminar. We have Sean Nixon from Applied Math, an advanced COSI student. He got his bachelor degree in mathematics from University of Central Florida, and he's working in his PhD with Professor Mark Ablowitz. His interests include nonlinear waves, optics, and asymptotics. So, welcome to be
Hi.
the speaker today.
All right. So, I'm Sean Nixon. My advisor is Mark Ablowitz. Sarikas was the guy working on mode-locked lasers before I got around, and Yiju was the guy working on Soliton interactions before I got around, and now part of the talk will be on mode-locked lasers and Soliton interactions together. So, talk quickly about what I'm talking about when I'm talking about solitons and mode-locked lasers. We'll have a model for how the mode-locked lasers should go mathematically. We'll talk about perturbation theory, which is how I take simple solutions and use them to find more complex behavior. And we may not have time, but if we do, I'll talk about dispersion managed systems. So, here's what we're looking at for a soliton. I have some light waves, which are these red lines, the carrier. They're the teeth on my soliton. There's some tens of thousands of these teeth in a physical system. But the point is, I have this envelope which goes around the outside, and that's my soliton, is that localized pulse. And here, the velocity of the inside carrier waves doesn't have to be the velocity of my larger soliton wave. So this envelope is modeled by the nonlinear Schrodinger equation, and the soliton solution is a special-looking solution to this equation, special solution. And I want more than just a pulse. I want a pulse of a particular height. That's what I mean by mode locking. I want the same pulse every time. I don't want just any pulse. So what do I need? I need amplification, which is provided by stimulating conditions in some gain medium in my system, and that will make the soliton bigger. And I need some damping, which is provided in the laser cavity, which then makes the soliton smaller, and I need to do that over and over and over and over again. So on the long scale, my soliton will come to a particular height and width and speed. So here's an example of a system. This isn't the only way that I can make a mode-locked laser system. Here I have a pump. I'm putting more green laser light into my system because I'm, of course, have some loss, so I can't just run the same light around forever, and I'm taking a train of pulses out of the system. So my repeating comes from bouncing the light back and forth between these two mirrors. My gain is in this Ti sapphire crystal, and then everywhere else I have my cavity X-ray. I think here the mirrors provide most of the loss, and this is just from there. So my light goes back and forth, and I get a steady pulse train, all the same pulse, all the same different distance apart. And what can I do from this? Some general applications. I can use this to make a more precise clock than an atomic clock, which is accurate 10 to the minus 15 seconds, better than that. Using control of chemical detectors, can be used in telecommunications, and since we're all imaging people, it can be used for coherence tomography and two-photon microscopy. Both utilize these mode-locked lasers to do imaging work. And perhaps the most important on a larger scale soliton is space travel.
Captain's log, stardate 45376.3. We're approaching the planet Balana 3, where a new method of propulsion known as the Soliton wave is being developed. I've been asked to participate in one of the first tests of this new technology. Data. Data, isn't this exciting? We are going to witness a moment in history. Every nanosecond in this continuum is a moment in history once it has elapsed.
No, I mean, we are going to see something that people will talk about for years. I mean, think about it. No more monkey warp engines or nacelles. A ship just generates a soliton wave and then rides it through space like a surfboard.
We aren't quite to that application as a realized matter. So I talked about I needed a gain and I needed a loss. This is the house model, the first attempt at modeling mode-locked lasers. Here's my gain. I have just a linear gain. Psi is my envelope. This is an extra filtering term that's chopping off the higher frequencies. And this collection of terms is my loss. I see I have a linear loss, but to really get mode locking, they also have a then cubic gain, cubic gain. And it's not I just put in a bigger pulse and I get a bigger gain. At some point, there's a saturation to the gain system. I put in a big enough pulse. Eventually, the gain in the system and the loss in the system, as we'll see, tapers out. So where does this come from? I have, and a two-level meaning, the loss should be proportional, or the change and loss should be proportional to the loss and the magnitude. But if this happens very quickly, so that would be for the time it takes to make these changes very small, then I should go exactly to my equilibrium solution. So this is an equilibrium solution to the differential equation in Z. And then what House does is he assumes that this term, the intensity over the essentially the power that the system saturates at should be small, and then you expand it. But this is one step more complicated than we really need. The idea behind this was if I expand it, I can then find an exact solution to the equation, and I can do some math behind that. And that was fine 40 or so years ago. Now I can do math a little better, or a little differently, and I'm going to take out that last step. I'm just going to have, now I see here, my gain is saturated over the energy of the system. This is the normal phi. And here my loss is only saturated against the intensity. And I've make a quick change of variable, so now here it is. Now I'm going to call it the power energy saturation model. So it's pretty much the House model, the original model. I'm just treating loss a little bit more complicated. I'm not making the same simplification because I can deal with this now. So what do I have? This is that SESH solution I told you about, was a special solution to nonlinear Schrodinger equation. This is the general profile I see here is a SESH. This would then be the velocity of the soliton, and this is the way that the velocity appears in the phase. And as I say, this is the numerical soliton and the asymptotic soliton. So this is numerically, I mean, this is a numerical solution of the PES equation, not just an NLS. So this is a numerical solution of this equation. And this is my analytic guess based on it having a general soliton form. What it does is I'm going to let the parameters eta, which corresponds to the height, v, which is the velocity, t naught, which is the center of the soliton, and sigma, which is any extra phase contribution in the soliton. I'm going to let these vary slowly in z. These terms are smaller. The nonlinear Schrodinger equation is the dominant force. These terms are small, so in practice, the gain, the tau, and the loss are small terms, and when taken together, they're a small contribution. So I have my soliton solution, and then I'm going to let it evolve essentially slowly in its main parameters, and that will tell me how the soliton evolves in my mud-lock system. So to do this, I'm going to require that my soliton solution, now that it has slowly varying parameters instead of just constants, I'm going to say those constants vary to satisfy these integral equations which are derived directly from the anomalous Schrodinger equation. Since f is small in our case, the right-hand side is small, and the differential equations all tell me that I'll have slowly moving parameters. So this is essentially a perturbed conservation energy, perturbed conservation of momentum. Not quite the conservation of the center of energy, but an integral relation about the center of energy. This is a mess, but it's the right mess. So, and it comes, I can derive it from the equation. So it's true, just a little more complicated. So I plug in my soliton form. I now have 4 parameters that are functions of z, and I just reduce all those integrals and take the derivative. Now I have a neat system of equations for how the parameters should evolve. And clearly here the easiest two are that there should be no extra shift in the soliton other than what comes from its velocity, and there should be no extra phase shift. And these are the equilibrium. See, the first equation, eta, for 0 velocity, I see here, this term is always going to be positive. I always want a positive height to my soliton. If I had a negative height, I would just change around the phase by 2 pi. So this is always a positive term. So then this is v equals some negative or dv dz negative constant times v. So that's always going to go to 0. And then once that's going to 0, eta has 2 equilibriums based on the solutions to this equation. One's positive, one's negative. I only care about the positive solution. So I have constants, v goes to 0, and eta is the equilibrium solutions for this equation. I can find that if g is less than L, the only equilibrium that's useful is 8 equals 0. That's stable. That means there's not going to be any mode-lock pulses in that case. If the gain is bigger than the loss, then I go to the equilibrium at 0 is unstable. So if I have any bit of pulse, it's going to evolve into a stable soliton. And this is an equation of eta z versus eta. I can see here are the equilibrium solutions, the positive equilibrium solutions that correspond to the mode-locked solitons. You don't have to take my word for it here. I've compared my numerical results to my asymptotic results. This is just for the peak of the soliton, which was the main interesting parameter moving around. I find I have excellent correspondence. Here's a case where the gain here, all the loss is 0.1. So here the gain is less than the loss, and I don't have any pulse. Everything goes to 0. After that, I can now think about 2 solitons. So one soliton interacting is easy. 2 soliton interacting is a bit more complicated. What I see is that this soliton really only sees contributions from the other soliton where this dotted line. So it's this tail area where the 2 solitons interact. That's the only real contribution. So the effect of my soliton on the right on the soliton to the left is small, which is going to be the same way that the effect of my gain and loss are small. Now the effect of the 2 solitons on each other is small. So then I write my equation. Here's the equation for phi1, and I can derive the term of how phi2 affects phi1. And then, so for classical NLS, this is NLS with no gain and loss terms, just 2 pulses sitting together, nonlinear Schrodinger equation, and how they interact. I get a new system of differential equations. Now, instead of just 1 eta, I have 2 etas because I have 2 solitons. So I had 4 parameters before. Now I have a full 8 parameters. and the distance between them doesn't change any more than the velocity would say. The phase between them doesn't evolve any more than this is the then phase between them. This is the distance between them. So delta t was the distance. So I have two centers. I'm just looking at the difference between them. I have two phases. I'm just looking at the difference between them. I have my two soliton interactions, which are small, and I have my gain and loss terms, which are small. So I'm going to treat them, just add them together. Now the equilibrium for two solitons, before this would have been the energy of one soliton, which would have been 2 eta. Now it's the energy of two solitons, so it's 2 times 2 eta. Same here in the filtering term. And the loss is the same as it was before. The intensity isn't a non-local term. It's just a local term. So the intensity is just the intensity of whichever local soliton I care about. So here's my predictions up against the numerics. What I see here are the contour plots. So these big multicolored stripes are the soliton, and then the dotted line, my asymptotic prediction for the center. So this is how the solitons were going back and forth. Here I put in an initial phase of 0, so they're in phase and they attract each other. Here I put in an initial phase difference of pi, and they repel each other. Here's a case where I didn't just do pi or 0. So it initially attract each other, and then they repel each other. And here's the evolution of the difference in phase numerics against the asymptotic. So I still have exceptionally good predictions of the numerical results. Here's a nice picture to show you that the solitons are still the basic asymptotic soliton state. The blue is the numerical solution, the dotted line is the asymptotics. Here's my equations that I was using analytically. This is the S1 and S2 are essentially just the terms that I had from the mode locking terms, and the sine and cosine part are the same terms I had for just the strict interaction of the solitons. And since there was no extra contribution to the center of the soliton, or the phase of the soliton from the mode locking, these equations are still, the change is based on the change in velocity, which is what you would expect. This is essentially the derivative of position is equal to the velocity, the net velocity between the solitons. So what can I do from here? Here I have contour plots of what's going on. Eta 1 being the height of the soliton on the left, eta 2 being the height of the soliton to the right. Here I have that the contribution from the interactions is significantly smaller. It's exponentially small as the solitons diverge from each other. So if I just look for how the mode locking contribution comes, I can see here I have an unstable equilibrium when the two heights are the same. Again, here loss is 0.1, so this is above loss, but not enough above loss. Here, after some threshold, I pump up enough gain. Now I can have those two solitons be a stable equilibrium. So for this gain, I wouldn't see two soliton solution. One of the solitons would disappear, and they would go to a solution here or solution here. Here, I have a nice equilibrium solution where I can have two solitons coexisting in the mode locking system. if I look at the evolution of the phase, I've taken here a bunch of different initial phase differences. In each case, I just start the solitons at the same height, but the general results are the same even for two solitons of different heights. It's just not quite as symmetric. But you see they're all going here, and this is pi. So I'm going to have two stable pulses. They'll want to repel each other, and they'll want to go to a pi phase difference between them. So I have how the phase between the solitons is going to behave. This is how the position between the solitons is going to behave. I have that my two heights are both going to be going at least close to the same height. So I expect that they're both going to the same eta star. That's what I saw here. The equilibrium is for the same eta in both pulses. And I saw that the phase is going to pi. So starting with that, I go to the equation for the difference between the change in velocity. Here, my sine of pi is just, or cosine of pi is -1. My etas are both eta star, so I just have the one height. If I differentiate on both sides the equation for the distance between the solitons, and I have a second order differential equation in terms of just delta E, since I can write delta V in terms of delta eta and eta, or delta C eta star. So now this eta star is some particular equilibrium that they're going to, so I can find that number. Now this is just a differential equation. The second derivative, this is all slowly moving, so the second derivative is much smaller than the first derivative, and now I just have a rather simple differential equation to solve. And the result of all this discussion is that I can now tell you that the solitons repel each other logarithmically. So while they do continue to repel each other forever, indefinitely, in a physical system, I might no longer see this since the distance between them is dying off logarithmically. So, went extremely fast. Here we have dispersion management. We'll go back to the original system real quick. This is all in pieces. I'm in the sapphire crystal at some point. I'm outside the sapphire crystal at some point, and the behavior of the light inside and outside the crystal differ. So I've been just taking it all together. That's what is going on in this differential equation. The dispersion is always the same. The nonlinearity is always there. Well, that's not really the case. So when I talk about dispersion management, I'm now going to consider the case where in some portion of my equation I have a dispersion that's negative. At some point I'm going to have a positive dispersion. So at some point my soliton is going to be focusing in, at some point it's breaking apart, and I'm going to have only the nonlinearity in my positive dispersion area. So I have the same perturbation again. This is all discussing how I take my general idea of these two dispersions. I don't want to solve the equation doing a piece here and a piece here. I just want to know, after one cycle of going through the positive dispersion and the negative dispersion, what comes out in an average. So this is then an equation for the average here. This is the essentially breathing of the soliton, contracting and expanding. And I'm going to just care about this part, which is the at each period around my system, what the soliton looks like. So pretty close to the same. I now have my nonlinearity a bit more complicated now in terms of Fourier transforms. But I can solve this numerically, and I'm comparing the initial, now this is the initial soliton I put in compared against the soliton after 500 units in Z. And I see that I still have solitons that aren't really moving away from each other. It's still right on top of each other. And here with the dispersion management, I'm actually getting close enough that you can really see that they're starting to really overlap a lot more strongly. So in a dispersion managed system, so I saw in the constant dispersion system, I can get two solitons that I would expect in a physical system would not continue to repel each other. They'd eventually just come to rest. And since I really have a dispersion managed system in a dispersion managed case, I can actually get those solitons much closer together without any interference. Here I have, and I mean an effective bound state. I'm going to go 500 units in Z and require less than a 1% difference in the distance between the solitons. So S is a measurement of how strong the difference in dispersions is. So as Z's get bigger, I have a bigger jump between the positive dispersion section and the negative dispersion section. So as I keep increasing that jump between where there's positive dispersion and negative dispersion, I see I can get my solitons closer and closer together. And these are some pictures of them getting closer and closer together. Here I have the phase. So I see as they're kind of farther apart, I have two chirped phases and two distinctly different chirped phases. Here they're starting to even out, and as I go to an even larger map strength, I have just one continuous chirp with a pi's phase jump in the middle. And won't discuss this. So I have mole-locking behavior found for a large range of parameters. The problem with the house model, which I gave you first, is that although it does have this mole-locking behavior, it's very sensitive to the parameter regime. Now with the PES equation, I have for practically I just need the gain is bigger than the loss is my only restriction. I find effectively stationary soliton strings, they move apart from each other, but it's drying off logarithmically. So effectively, experimentally, I would expect that I find solitons that are right next to each other. I can find similar behavior in this dispersion managed system, although I haven't found this analytically yet. I found that the interaction depends on map strength, so if I can continue to increase the difference in the dispersion from one piece of the map to the other, I can start to get those solitons closer together. And these are actually not moving apart from each other at all. These are locked in next to each other solitons, so that's slightly different than here these solitons are slightly moving apart from each other. It's just small enough not to notice. Here the solitons are actually locked into each other. So in a dispersion manner system, it might be possible to find just exactly locked in solitons. And I guess that's it. Are there any questions?
So we have time for questions.
So when you're comparing some of your results using your analysis with numerics, like what kind of schemes are you using to solve these differential equations, and how accurate are they? I mean,
I'm just using the built-in Runge-Kutta, the adaptive Runge-Kutta in MATLAB. I don't have any question that they're right. If I continue to increase the sampling of points that I have across in T, I can get the same results, so I expect that they're not a numerical problem. Yes?
So it seems like your equations apply to fiber soliton lasers directly, but the free space Ti-sapphire lasers, inside the laser, the soliton beast is really a multidimensional spatial and temporal soliton. Have you considered extending these kind of models in that direction to show apertureless mode locking and the other effects that are known to happen in Ti-saps?
I haven't worked on this much. The main idea was that instead of using the house, so there's a base model. I'm going to look at those by adding then more and more complicated terms to the nonlinear Schrodinger equation. So first, I'm looking just that this is a good first model. This is a good jumping off part, and it's better than the previous models. So from there, you can use the same, the analysis would all be the same, whatever extra terms you want to put on for the different phenomenon that you're seeing in the Ti-sapphire laser. But these are the two main points, right? I need something that's gaining the system and something that's adding a loss to the system. So I want to model the dominant forces, the forces that I need most readily to get mode locking first. So there's more work to be done, but
I mentioned that Cartman at MIT carried out a very detailed study numerical of this, the Ti-sap system, with modeling in twofold. And got good results. Multi-dimension remains to be studied.
Well, it's been studied numerically, but it's not being good analytic.
Multi-dimensions remain to be studied by us.
yes.
So I wondered if you've modeled any of the dynamics, like for example, in the laser, if you're cranking up the power going into the crystal, sometimes you can actually directly see this transition from a single pulse to a double pulse.
I have. So my initial study of pulse interactions came about because I found that if my initial pulse were badly distributed, let's say, a soliton has a particular height to width ratio. So if I make a soliton that's tall but it's not narrow, now it's too wide. I did find initially that the two solitons came out. The problem was that it was not numerically accurate. I saw the two solitons come out, but then if I changed essentially the number of points across that I'm taking, now two solitons come out, but they're not exactly where the two solitons came out before. So I expect possibly with a more clever numerical scheme that you would probably still see big pulses when you pump up the energy in the system splitting into two solitons. So yeah, I think that's there. It's just numerically a bit chaotic. So I haven't done that. But that's essentially where this work initially came out with. I accidentally put in pulses that were too big and two solitons came out, and then we want to know how to deal with those. which would further indicate that experimentally I should see double pulses in my system.
Any other questions? Okay, let's thank Sean again.
Yep.